Welcome to this introduction to the Apollo Guidance Computer, or AGC. I'm Chris, this is Toby, and we're going to present to you the technological marvel that is the Apollo Guidance Computer.
That's right, Chris. First, we are going to take a look at the hardware of the computer before showing you how to operate it on a mission to the moon.
The mighty Saturn V rocket, standing over 360 feet tall and weighing over 6.5 million pounds, is the largest rocket ever built. All its power is just needed to escape the gravity of the Earth. The actual spacecraft going to the moon is just a bit on top. Not one, but two computers are on board the vehicle. One in the command module, which is the primary spacecraft for flying to the moon and returning to Earth. The second unit is placed in the lunar module, or LEM, which the astronauts use to land on the moon and, after their stay, ascend back up to the command module. Both computers are physically the same, but are running different programs.
The Apollo Guidance Computer is a really remarkable machine. It comes with 36,000 words of memory, with each word being 50-bit long. Internal operations run on a clock speed of 1 MHz, which are 1 million cycles per second. And it features the latest state-of-the-art integrated circuits. Here we see a simplified block diagram of the AGC. The main components are the program counter, the selection circuits, the memory, which we will explain later in detail, the memory buffer, the sequence generator, the clock, and finally, the arithmetic unit, the heart of the AGC. Now, let me introduce you to some of these components in detail. The clock component provides a 1 MHz signal for the sequence generator. The clock's main components are a 2 MHz oscillator and a clock divider logic. The sequence generator then provides all the clocks and timers needed for the operation. A modern computer's memory architecture has two different types of memory, ROM and RAM. ROM means read-only memory. It's the part where the programmers store their software. It's permanent and cannot be changed during the mission. RAM, on the contrary, stores its data only temporarily, and its content can be changed during operation, which is vital for the computer to work. We will see how both types of memory are implemented in the Apollo Guidance Computer and how they work together. The Apollo Guidance Computer Random Access Memory, short RAM, is built the same way as in today's modern computers, magnetic core memory. Let us take a brief look at how this works. The memory is made of an array of magnetic cores, which can be magnetized and maintain their magnetization, even when there is no magnetic field applied. This means a magnetic core memory keeps its information even in case of power failure.
So this is how we can store data within these rings?
Yes, Chris. For simplification, let's look at only one of the cores. It can be magnetized in two different ways. We can either magnetize the core clockwise or counterclockwise. The choice which of the states represents a binary 1 and which a binary 0 is arbitrary. For this example, let's define this direction as binary 1 and the other direction as binary 0. In order to apply the magnetic field needed to change the core's magnetization, we must thread a wire through the core. We shall call it the select line. Later we will see why. When we now apply current to the wire, we can magnetize the core. In this case, it stores a binary 0. As soon as we reverse the current, the magnetization changes and the core now holds a binary 1. Now that we know how to write data to the core, we can continue with how to read data from the core. To achieve that, we have to thread another wire through the core, the sense line. At first, we will write a binary 1 to the core. Now the readout process begins. The first step is to apply a current to the select wire, so that we write a 0 to the core. As the magnetization changes, a voltage pulse is induced in the sense line. However, the core does no longer hold a binary 1, but a binary 0. The readout is destructive. The next step is to restore the previous state by reversing the magnetization again. This step must be done every time we read out the core. When the core originally holds a 0, again we write a 0 to the core. But because the core already stores a 0, there is no pulse on the sense line, which is interpreted accordingly. In the next step, we would again apply a reverse current, as we did when we read out the binary 1. In order to prevent that, we write a 1 to the core supposed to hold a binary 0. We must thread another wire through the core. It's called the inhibit line. After the 0 is read out, we again try to write a binary 1 to the core. But we also apply a current on the inhibit wire in the opposite direction. The magnetic fields cancel each other out, and the core's magnetization remains unchanged. Now that we know how to write and read one single bit, let's take a look at how to handle multiple cores arranged in an array. As it's feasible to only address a single core at once, it's sufficient to use only one sense line for the whole array, which is weaved diagonally through the array. At next, a modification of the select lines is needed. If we did apply a current to one of them, all the cores in a row would be magnetized at once. To overcome this problem, we add vertical select lines to the array and split the current needed to change its magnetization in half. Now a single selection line is too weak to magnetize a core. By this, we can select the core we want to read out by the crossing point of the selected vertical and horizontal selection lines. This is also the reason why this type of memory is called coincident current core memory. The Apollo Guidance Computer's read-only memory uses latest state-of-the-art memory technology, core rope memory.
What is core rope memory, Toby?
Good question, Chris. The most able scientists at MIT developed a way to permanently store code using magnetized rings made of a special alloy. Here we have a ferromagnetic torus, just like in a transformer. We can magnetize it by applying a magnetic field. For this, we can use a simple copper wire, on which we apply a current. Let's take a closer look at how this type of memory works.
For the sake of simplicity, let us assume our memory is composed of only 4 cores, which are all made of a special ferromagnetic alloy, called permalloy. They are not permanently magnetic, but as I said, they can be magnetized when current flowing through the set reset wires create a magnetic field. In order to magnetize only one of the cores, there are so-called inhibit lines, which prevent a change of magnetization in the cores. Now, let us change the magnetization of core 1. At the start, the magnetization of all cores is the same. Now we apply a current on lines 1 and 4. One can see that cores 2, 3 and 4 are threaded by at least one of them. Core 1, however, is not threaded. At the same time, we also apply current on the set reset line in the opposite direction. As a result, the magnetic fields in core 2, 3 and 4 cancel each other out. Because core 1 is the only one threaded by the set wire, its magnetization changes according to the direction of the set wire's current. Before we go on to the next core, the current in the set reset wire is reversed, and core 1 returns to its original magnetization. The other cores, on the contrary, are not affected, because the magnetization is already saturated. In order to change the magnetization in core 2, we must switch on inhibit lines 1 and 3 at the same time the reset set line. Again, only the core we want to magnetize is not threaded by the inhibit lines, and thus the magnetization of core 2 changes due to the current in the set reset line. After the reset, we can do the same with core 3 by putting current on inhibit line 2 and 4 and the set reset line. And finally, we can alter the magnetization of core 4 by using lines 2 and 3 and the set reset line. Now that we can control the magnetization of each core individually, we can take a look at how to store and read out data using the cores. At first, we rearrange the inhibit wires, so that we have enough space for additional wires. Now we add another wire, the sense line. One can see that it either threads a core or passes next to a core. When the sense line threads a core, it represents a binary 1. When it passes the core, a binary 0. 0 for passing, 1 for threading. If we now reverse the magnetization of core 1, a current will be induced in the sense line. The resulting pulse is interpreted as a binary 1. Let us continue to core number 2. Here, the sense line does not thread the core. Due to the form of the toroid, there is no magnetic field outside of it. So, no current will be induced in the sense line. This is interpreted as a binary 0. The same happens as we continue to core 3 and 4. Core 3 stores a binary 0, and core 4 stores a binary 1. However, for the mission 1 bit per core is not enough. Instead of threading only one sense line per core, we can also thread, for example, 16 lines through one core. Now one core does not only contain 1 bit, but 1 word. And we can read out the whole word by changing the magnetization of only one core. In the Apollo guidance computer, a core can be threaded by up to 64 sense lines. So each core stores 4 words.
This memory, however, is read-only, meaning once it's manufactured, changes are very difficult. During the mission, it cannot be changed under any circumstances. This, on the other hand, is also its greatest advantage. The robust design can withstand the enormous stress during launch and in space.
Now that we know about the memory hardware, we will have a look at how data is represented within the computer. The basic memory unit is a word. It contains 15 bit plus 1 parity bit. Every time a word is loaded from memory, a circuit checks whether there is an even number of ones in a word. The parity bit is always set in a way that it makes the number of ones even. When the 15-bit word contains, for example, 9 ones and 6 zeros, the parity bit will be set to 1, so that the total number of ones becomes 10 and is thus even. Basically, there are 2 different kinds of words: instruction and data words. An instruction word is divided into 3 parts: the parity bit, the operation code, or short opcode, and the address bits.
The 3-bit operation code shows which of the instructions is to be used.
The address bits point to a memory location, which we will explain later in detail. The data word also has a parity bit, while the other 15 bits are used to represent a value. The sign of the value is also indicated in a separate bit, using a so-called ones complement representation. We can also use 2 data words together to achieve double precision. When we use a data word in the central register, the parity bit already has been checked for. The position of the parity bit is now used for an additional sign, which is used to indicate an overflow, which can happen when we, for example, add 2 values. This table shows how the combination of both bits is used to represent both sign and overflow. As mentioned before, 12 bits of an instruction word are being used for addressing. This allows for a total 4096 memory locations to be addressed. However, this number is way too low to fulfill the requirements necessary for the mission.
But how can we access additional memory when there are only 12 bits available?
The engineers came up with a genius solution: memory banking. Let's take a look at how this memory layout was designed.
Here we see a diagram of how the different memory addresses were separated. The 12-bit memory address is given an octal pseudocode, which goes from 0 to 7777, which would be 4096 in the decimal representation. The first addresses are called the central registers. They are reserved memory locations, which we will explain later in detail. The memory area up to octal 1377 is called fixed erasable memory. These are made from coincident current magnetic core memory, as we saw before. The next area is also RAM, but this area is banked. The next 2 areas of locations are both read-only memory: the common fixed memory, which is also banked, and the fixed read-only memory, which is not. There are 8 banks for the switched erasable memory and 36 banks for the common fixed memory, which extends the memory of our computer from 4096 to more than 36,000 works.
That's amazing. But how does the programmer select the bank he wants to use?
Good question, Chris.
Banking means that multiple memory locations have the same address, but are located on different memory banks. When addressing a banked memory location, The programmer must choose the bank he wants to use. The programmer has 3 different addresses in the central registers where he can set the number of desired banks. They are not made of magnetic cores. Instead, flip-flops made from integrated circuit NOR gates are used. This is why the registers do not have a total of 15 bits. At address 003, there is the 3-bit erasable bank register, used to switch between the 8 RAM banks. At address 004 is the 5-bit fixed bank register, used to switch between the 36 read-only memory locations. At memory location 006 is the both bank register, which can be used to set both banks simultaneously. Whenever a programmer writes to either the both bank register or to one of the others, the content gets automatically copied to the corresponding register. This, of course, works also the other way around.
But wait, the 5 bits of the fixed bank register can only address 32 banks. Didn't you say there are 36?
That's right, Chris. To address all of the fixed memory banks, we need to set another bit, the so-called fixed extension bit, or superbank bit. Now we have in total 6 bits to refer to the fixed memory banks, which is more than enough. At next, we want to present the heart of the AGC, the arithmetic unit, made of 8 special registers. As we have seen before, they can be found at memory addresses 0 to 7. We have already seen 3 of them, the bank registers. Now we want to show you the rest of them.
At address 000, there is the accumulator. It is used for arithmetic operations, like addition, subtraction, division, or multiplication. When we load the data word into the register, bit 16, the parity bit, becomes a second sign bit to indicate an overflow. Therefore, we have at address 001 the L register, or low register. With both registers, we can have double precision. The next 2 important registers are the Q and the Z register. The Z register is the program counter. When we execute a program, we have to store the address of the instruction we want to execute next. Whenever we want to call a subroutine, the content of the Z register will be stored in the Q register. When we return to the main program, it will continue at the address stored at the Q register.
You already know about the next 3 registers. They are used for memory banking.
The last of the special registers is not associated with any storage. When we read it, we will only return zeros.
The programmer can now write programs by sequentially using instructions. There are 36 instructions in total. Each instruction is giving a unique opcode. Now we would like to introduce some of the basic instructions, which are available to the programmer. For example, the divide instruction. It is known to the programmer as DV and has the opcode 11 assigned to it. The content of the accumulator is divided by the content of k, leaving the integer result in A and the remainder in L. The operation takes 6 machine time cycles, which are roughly 27 microseconds. The programmer must be well aware of this. These instructions require the use of an extra 16th bit called the extra code bit for opcode definition. Another example is the square instructions. It takes the contents of A and multiplies again with the content of A. Now you see the Apollo Guidance Computer's hardware and how it's programmed. Let's move on to how the computer is operated.
The computer is operated by this display and keyboard device, called DISKey. This interface acts as both output and input, which means it allows the astronauts to talk to the computer and vice versa. Interaction with the computer is carried out by using combinations of verbs and nouns, just like the English language. They are identified by a 2-digit number. Here is a list of all possible verbs and nouns, which are also used by the astronauts. For example, to display the current mission time, the astronaut enters verb 6 for display and noun 65 for time in hours, minutes, and seconds. Some verbs are reserved for the computer to request action by the astronauts. They cannot be input into the DISKey. Programs, like verbs and nouns, are identified by 2 digits. There are over 40 different programs. A program can be loaded manually by the operator or automatically by an already running program. To load a program manually, verb 37 is used. The noun in this case will be the program identifier. During critical parts of the mission, for example, re-entry, programs are usually only switched automatically by the AGC. The disk key consists of several lamps called condition indicators, a numeric display for program information and data, and a 19-button keyboard. Data is input using the verb and noun keys, plus, minus, and the number keys. Enter is used once an entry is complete. If a wrong number was input, it can be cleared by the clear key to start over. The pro key, which stands for proceed, is used when the AGC asks if it may continue with the next step of a program. This occurs especially in programs with complex maneuvers, like for example, calculating engine burns. The disk key shows the values the computer intends to use. These can be accepted or changed by the astronauts. Pressing proceed allows the program to go on. The proceed key is also used to confirm engine ignitions and for powering down the AGC. The condition indicators are directly controlled by the software and inform about the current status of the computer as well as warnings or errors. Uplink activity lights up when the AGC is remotely controlled by ground controllers in Houston. Since the primary source of guidance and navigation data is an Earth-based tracking system, Mission Control regularly updates the AGC with the newest tracking data. Other elements, like the system clock, can also be changed remotely. As long as this light is on, the disk key cannot be used by the astronauts. The next three lights are warnings about the inertial measurement unit. The IMU is only operational within a narrow temperature window. If it gets too hot or too cold, its readings lose precision, and in the worst case, it gets damaged and needs to be shut down. If for several possible reasons the IMU cannot deliver the current attitude of the spacecraft, no AT is illuminated. Finally, the gimbal lock indicator warns the astronauts that the middle gimbal of the IMU is at a critical angle greater than 70 degrees. If the deviation exceeds 85 degrees, the IMU loses the ability to track the attitude. If a gimbal lock happens, it needs to be reset manually with a rather complicated procedure. The AGC can be put into a standby mode to conserve power while it is not needed. As long as the computer is in standby, the standby indicator is illuminated. The next light is the program alarm for whenever a software or hardware error is detected. Sometimes a restart of the AGC might be required to resolve the issue. If a restart is necessary, restart is illuminated until it is complete. Operator error indicates that invalid data has been entered in the previous entry. This could mean that the verb-noun combination does not exist, or that the data entered did not fit the required format. The reset button needs to be pressed to clear both program alarms and operator errors. Although the AGC is capable of running several programs in parallel, only one can ever be interacted with using the disk key. Whenever another program needs to display information, the key release light comes on. Pressing the key release button on the keyboard allows the AGC to switch to the waiting program. Until it is pressed, the astronauts can continue working on the currently shown program. Finally, the tracker light indicates one of several errors regarding the location or orientation of the spacecraft. The specific errors are different in the command and lunar modules. The LEM also has 2 additional velocity and altitude warnings regarding bad landing radar data. Because of the complexity of the mission, some of these indicators also have further meanings in special situations. But since this is a basic instruction, you don't have to worry about that right now. Let's go back to our example of accessing the current system time. Remember, to display the time, we need verb 6 for display. and noun 65 for the time. The verb key is pressed, followed by 0 and 6. Then noun 6, 5, and enter. A short moment later, the time is shown in the display. Hours in the top row, minutes in the middle, and hundredths of a second at the bottom. Had we used verb 16, which is called monitor, the disk key would continuously update the time about every half second. Now that we have seen how the AGC is operated, let's look at a typical flight to the moon. This schematic shows all critical events on the way to the moon. In most events, the Apollo guidance computer performs important tasks. We will now follow a typical mission. Before liftoff, the flight's backup crew is in charge of powering up the spacecraft, including the Apollo guidance computer. Several self-checks are completed by the computer to ensure its readiness, including checking the integrity of the core rope memory, where all the programs are saved. Now the first program, Program 1, is activated to initialize the inertial measurement unit. The AGC then switches to Program 2, waiting for liftoff. At the moment of liftoff, Program 11 takes over and starts the mission clock. For the duration of the launch, which takes about 12 minutes, the Saturn V rocket is flown by its own computer, the LVDC Launch Vehicle Digital Computer, housed about here. The AGC is merely a passive observer. Current flight parameters like speed and altitude are shown on the disk key. After a successful launch, the final stage of the rocket is in a parking orbit around the Earth, waiting to burn towards the moon, the so-called translunar injection. This second burn of the third stage is set up and monitored by the AGC, but the execution lies again with the rocket's own computer. The command and service module, as well as the LEM, are now on a trajectory towards the moon. The final rocket stage is discarded. Every critical action from now on is performed by the computer, for example, mid-course corrections and entering lunar orbit, using the command module's rocket engine. The most dangerous task for crew and computer now lies ahead, landing on the moon. 2 astronauts board the lunar module and decouple from the command module. The lunar module has its own AGC with separate programs for this task. Descent down to the surface is split into 3 phases: braking, approach, and landing. The crew starts Program 63 for the braking phase. For now, it's just about slowing down from orbital speeds. At about 7,000 feet up, the AGC automatically switches to Program 64, approach. Altitude and velocity are now shown on the disk key. The LEM is closing in on the landing site, guided by the computer. If anything goes wrong, a separate computer, independent from the AGC, is ready to abort and fly back into orbit at any moment. The final landing is flown manually, but still greatly assisted now by Program 66. Our astronauts are now on the surface of the moon. Another critical task is, of course, returning from the moon to rendezvous with the command module. The LEM's AGC calculates the path to meet the command module in orbit using state vectors of both spacecraft and distance from the LEM's rendezvous radar. The final challenge for the AGC on board the command module is the return to Earth. Before entering the atmosphere, the service module is jettisoned. Only the return capsule remains. The splashdown location is confirmed with Program 62. Falling towards Earth, the AGC switches to Program 63, waiting for the atmosphere to start decelerating the spacecraft. Once the air is thick enough, at about 300,000 feet up, the capsule starts to slow down. Program 64 handles the re-entry. The capsule can angle itself in the airflow to provide lift and extend its flight path, or simply fall down, which is called ballistic flight. The AGC uses both programs, 65 and 66, to reach the landing site. As you can see here, after the first re-entry phase, the spacecraft typically rises within the atmosphere before descending again. The final steering towards the splashdown location is managed by Program 67 until the parachutes deploy and the capsule lands in the Pacific Ocean. The AGC has done its job, flying up to the moon and heading back home. It is often called Apollo's fourth crew member because of its critical importance to the mission. And our 3, nay 4 astronauts have returned safely from man's greatest adventure.